and that's why it's A and C. All right, so to finish up the lesson, besides perspective projection, there are other types of projection operators, which in fact are sort of special cases, and they're used sometimes, so they're worth mentioning here. One interesting form of special case of perspective projection is called orthographic. And as it's drawn here, basically orthographic is when I take my world and I just smash it right into my image plane. And what's interesting about that is it actually can be thought of as a special case of perspective projection, but where the distance from the center of projection to the image plane is infinite and my object is infinite. Right? If those both were sort of infinite, then basically what I end up doing is the z value doesn't matter because those rays are parallel. So that's why this is also called parallel projection. And so xyz just gets moved to xy. This is actually sometimes used as a model for telephoto lens, because telephoto lenses are looking at things very, very far away. So all of your rays are almost exactly parallel. Now, of course, it has to be scaled. And so you end up scaling the x and scaling the y, but it's the same scale value for your whole world. I mentioned that because we're going to talk about something called weak perspective in a minute. So basically, when you throw away the z value and then you just scale the x and y by some number, that's this parallel projection. And since I said it was a special case of perspective projection, there must be a matrix operation that would recover it, and here it is. And you'll notice now that this value is 0, okay? And this value is 1. So xyz1, the matrix just equals xy1, and when you divide out by the 1, you just get the xy. So even this orthographic projection can be represented as the same matrix, as a matrix multiplication when we use homogeneous coordinates. Another model is called weak perspective, sometimes called scaled orthographic, but that's a bad choice. There's also something called paraperspective, but what we're going to call weak perspective is the following. The idea is that we know that when things get further away, they're going to get smaller. But what we're going to do is we're going to say that all the points on a given object, we're going to assume they're all at some constant depth. We'll say z0 as is written here. Okay? So for all the points on that object, xyz will get mapped to fx over z0, fy over z0. So that object will get scaled. But some other object, might be a significantly closer object, it will get scaled by a different value. So basically in weak perspective, what we're saying is that the difference in depth over an object, or over the range of an object, is very small compared to the distance in depth from the object to the center of projection. And if that's true, then you can basically say that each object has its own scale factor. Of course, as a special case of perspective projection, we can do this in a matrix form also. So here we have the equation or the transformation we said before. xyz goes to fx over z0, fy over z0. So basically f over z0 is acting like a scale factor. Okay, so here we have our projection matrix, which now, instead of having a 1 over here, has a 1 over s. And then when I multiply that through on the homogeneous coordinates and then divide, I'm dividing by the 1 over s, which gives me sx comma sy. So weak perspective gives you this scaled effect of each collection of points that sit on a given object. So those are the three camera projections that we'll talk about. The one that we'll use all the time is perspective, which ends up giving you fx over z, fy over z, and we showed you how to do it in matrix coordinates using homogeneous coordinate system. And then we also talked about weak perspective, where you have a scale factor sort of per object, or orthographic, where you basically just throw away the z value. All right, so that ends this lesson on projection. We're going to use the perspective projection a lot, so get to know and love it. And by the way more math is coming, so fasten your seatbelts.
Anamorphic images are ones that require the viewer to look from a particular viewpoint to show the desired visual. Other perspectives usually yield a stretched or distorted result. Artists use their knowledge about perspective projection to create some amazing illusions, like this Lego army designed by Leon Kier. Viewed from any other angle, it looks strange. This art activity popularized by Myrna Hoffman uses a curved mirror to undistort a flat drawing. Can you find other cunning examples of people hacking perspective projection? Share with your peers on the discussion forum. I encourage you to create your own. It's a lot of fun. Check out this excellent Instructable from Mr. Grease Tattoo for some inspiration.
Hello, welcome back to Computer Vision. Today we're going to start talking about stereo, and this particular lecture is on stereo geometry. In general, the next few lectures are going to be on the relationship between sort of camera geometry and scene geometry. We're starting with stereo because, frankly, you guys are going to do this in a problem set, and I want to be able to get you there quickly. And also, in some sense, it is the conceptually easiest way to get started. So stereo is really just a special case of having multiple views of an image, two particular views. And here's just an example of two views of a vase. In fact, we're going to get to this particular figure a little bit later when we talk about epipolar geometry. But the idea is that there's this relationship between two views, and you can use it to recover the depth that's there. We'll also take a look at sort of having arbitrary different views. This is an image that comes from work on using special features to align objects and be able to detect that they're there. But again, you have two different views and you have to figure out how they relate. This is an example of what you can get from stereo. So the picture on the left is one half of a stereo pair. On the right is a crude depth map. The brighter things are, the closer they are. In fact, we're going to talk about how to compute exactly that. And in general, you can have lots of views where you have images taken from a whole bunch of places or a whole bunch of directions, and it's a question of how do these images relate. And this notion of how images relate and how do they relate to the scene, that's what we're going to be focusing on. So the first question to ask is, well, why multiple views? Obviously, structure and depth are fundamentally inherently ambiguous from a single view. Remember, we're projecting from 3D to 2D. When we do that, we lose information. So here's an example of a man pushing the Leaning Tower of Pisa over to make it lean even further, and either he's very large, the building's very small, or there's an ambiguity when you project from 3D to 2D. Or how about, so those of us who grew up in the States were a fan of It's a Great Pumpkin, Charlie Brown. So that might be a picture that looks like this, which would be really a great pumpkin. But of course, what's really going on here is that the location of the camera makes it such that this picture just appears like the pumpkin is very large. You know, what's the fundamental problem? Well, the fundamental problem comes from perspective projection. Here we have an optical center, all right, and we have several points, such as P1 and P2, projecting along the same ray. And of course, because they project along the same ray, they land in the same spot, P1 prime, P2 prime. And so that's where the ambiguity comes from. And the question is how to figure out where P1 and P2 really are. And the trick, of course, is going to be to look at a different camera.
When you look at an image, what properties indicate differences in depth or provide hints about an object's shape? Think about various features that convey structural information in a scene. Stereo is not the only thing at work. After all, you are seeing these images on a flat display. Type in depth and shape cues you found as a comma-separated list. Feel free to look at other images or just around yourself for ideas. Some depth and shape cues I could think of are shadows, texture, focus or blur, parallel or converging lines, lighting, shading, objects occluding each other, and size and scale of objects.
So before we do think about how we're going to do this in a machine, what about humans? How do humans see in 3D? All right. And frankly, we can actually do this using just one eye before we even get to two eyes, because we look at these different cues. So here's an example. So when you look at this picture, in fact, when you look at any flat picture on a piece of paper or on a single screen, there is only flat real depth, and yet you see the depth that was in the scene. So here we have perspective effects. You assume that those houses are all the same size and that they're fading off into the distance is what makes them smaller. So you perceive depth from this perspective effect. Shading, here's a picture on the left, and B and C are some of the recovery of using an automatic method to try to recover the depth, and it's using just the shading information. You assume that the skin has a particular type of reflectance, and your brain figures out the depth in it. By the way, this is why certain kinds of makeup is used, right? By changing the shading on the cheeks, you change the apparent shape of the face. Even though, of course, you didn't change the face, you just changed the reflection. Texture. Here you see a wall, and you can tell that the wall is sort of curving around, and that's because the texture elements on it are changing. Those circles with the little lines on them, that's an early attempt at being able to recover orientation from texture. A more recent piece of work done by Lowe, here you have a picture, you see the strawberry, and you see the texture, and the texture changes as the surface tips away from you. And the system actually works on trying to recover the surface height or the orientation from the change in texture. And here's a really cool one. Remember we talked about that in real lenses, there's a single focal plane of depth. That is, there's some plane out there in the world that's at depth, that's in focus on the image plane. And the more you're away from that particular location, the more out of focus you become. So you might be able to take how an image changes focus as you change the aperture. Remember, a very tiny aperture, everything's in focus, and as you open up the aperture, the depth of field shrinks. And that means that things that are further away from that focus plane get fuzzier faster. So you could actually take multiple images from that same point, change the aperture, and figure that out. So it's a little bit of a cheat, because yes, it's one eye, but it's multiple pictures. All right. Here's an image of them recovering a 3D shape and depth from defocus. And the last one, and this is something we're actually going to look at a little bit later, and in fact it's actually related to stereo, is the idea that from a single eye, if something moves, you can tell the shape. Now, here's a picture of a statue, and it's pretty hard for you to figure out the motion that you would use. Mostly you're looking at the shading. So here's a simpler example. All right. Now, if all our video gods are working right, and the web is working correctly, and you've got decent bandwidth, and the moon is in the sun with the 7th house of Jupiter, whatever that is. Anyway, you should all be seeing a rotating cylinder. Now, some are going to be seeing it rotating counterclockwise, and some are going to be seeing it rotating clockwise. And that's because you can't be sure whether the dots moving to the right are in the front of the cylinder or in the back of the cylinder. But the idea is, purely from motion, you are seeing this cylinder rotate. It's pretty amazing, actually, if you think about it. And we'll talk a little bit about structure for motion later on in the class. But the idea is, from a single image, but the thing moving, you can get depth. We're going to come back to that in a minute, because it's a single image with the thing moving. Well, we can also have two images where the thing stays the same. These general methods of estimating shape from some cue, shading, texture, focus, etc. For a long time, that was a big deal in computer vision. It was called shape from X, sort of very popular in the late 70s, early 80s, which I know is prehistoric history for most of you. But the fundamental idea was that from an image, and from some assumption about the nature of the world, like that those houses are all the same, and therefore they're probably getting further away, the brain could compute depth, and we wanted to build machines that could do that as well. But we, and a lot of other creatures, have two eyes. So that we call stereo. And in stereo, the key is that the image from one eye is just a little bit different than the image from the other eye. Here I see the right side of Megan's nose, and here I see the straight part of Megan's nose. Megan's nose is pretty straight. Mine's crooked. Anyway. So you can think of stereo as recovering the shape from the motion that's between the two different views. And the idea is to infer that 3D shape. Before talking about exactly how to do that, people have been looking at this ability of the human brain to do this for a long time. And in fact, one of the cool things that showed up was stereo photography. So Charles Wheatstone, back in the early 1800s, invented the first stereo viewer, all right, where you would take two pictures and then put them through lenses so that each eye saw a slightly different picture. All right. So what you've got here is this wooden thing that prevents the image in the left eye from being seen by the right, and likewise the image in the right eye from being seen by the left. And there are these lenses here that essentially train the eye right on the image that's right in front of them. People were fascinated by this. So here's a picture of Abraham Lincoln taken in 3D. So we went from 1838 to 1860. so just 20 some odd years, and already you're doing 3D portraits of the President of the United States. So it became a really compelling thing for people to see, because you take this flat thing and all of a sudden you would see depth. Here's a stereo pair of Thomas Edison, most famous